Hello everyone, and here we are group 8 and we have the presentation on heart disease prediction using big data tools, and I am accompanied by Nikhilaj Rinde and Harshal Fegde and guided by Harshali ma'am. So this is the outline that we are going to cover, that is introduction, little survey, gap identification, problem statements and methodology, requirement analysis and everything that you see here. So introduction. So basically, heart disease can be a range of conditions like coronary heart disease and arrhythmia, etc. This all. Coronary heart disease involves the reduction of blood flow from heart muscle due to buildup of plaque and in the arteries of the heart. And in the most form of the cardiovascular disease, that is coronary heart angiogram, that is we find angiogram as one of the main we find angiogram as the main source, and currently there are currently invasive coronary angiogram is the gold standard for finding the presence of the clots, their location and the severity. However, the diagnosis method is costly and associated with morbidity and mortality in CAD page and in coronary arthritic disease. So therefore, this is the least invasive method, and but the diagnosis accuracy for this test is between 35 to 75%. So this, as you can see here, as you can look at here, that is the numbers here in study at Lancet. We can see that 2.1 million. As you can see in Lancet, that 2.1 million death in India. Total death 1.3 million are of cardiovascular death, and in 1.3 0.9 million, that is 66% were caused due to coronary heart disease. Here is the another headline from Times of India, which shows 34% death from related to heart disease. Business Standard shows that 28% death due to heart disease. So we can draw the conclusion that almost a quarterly of mortality rates are caused by heart disease. So here is the literature survey that we have done from 2015, that is taken from the K. Saxena and author R. Sharma, and we have used the techniques J48 naive bias from 2015 and references, that is SVM, decision tree, KNN, and J48. This all are the literature that we have done till 2021, and we predicted out SVM out, that is logistic regression perform better. So first of all, gap identification. As you know, gap identification that you can see here is that when we go there is many insurance company in India, that is LIC, ICICI, Tata AIG and etc. Let's discuss how LIC gives the insurance. First, LIC gives you approach to LIC gives you a questionnaire regarding personal details, medical history or family history. For example, did anybody in family suffer from heart illness, etc. After this, they send you to doctor associated with LIC and they send you to the LIC and to get a checkup, and if the doctor is satisfied with your result, then he or she gives you an health insurance. But even after this procedure, the cover of the heart disease is for the major related surgery, that is angiogram, is 30 to 40% only. So there is need for a revolution in insurance sector, which can be more flexible and robust only towards the checkup, but also towards coverage. With this project, we will be able to predict the possibility of having heart disease. So your medical insurance company can give you a more detailed and an customized policy prediction. So here is the proposed system. We propose that we saw that the current system is very slow, and with the use of machine learning and big data tools, we automated the system, and we are saving the both time and the resources, because it takes very less time to handle out these things. And this is also ensure the proper handle of data and also development in the medical field as well as insurance sector. So what is exactly our problem statement? So our exactly problem statement is that there is to predict the possibility of having non-invincibly, that is what is, so you might be asking thinking that what is non-invasive, that is without drilling a hole in a body. So this was the motivation behind our project, and the objectives that we are going to achieve were to develop machine learning models to predict the possibility of classification model, and to check the reliability of the data of the big data tools, and implement a proposed solution, and to determine a significance based patient report. And so this all you will see in the development part that we have developed. So from proposed methodology, so from here, proposed methodology, that we are collecting a data source from patients, that is the patient side, and the data is stored in data warehouse, where the data afterwards is analyzed through the machine learning models and predictions, and the doctor or the patient gets the report in the report form, that is in the tableau or something. So here is the next that is automation part that we have done, that is in AWS, that is we use Google Sheets, Amazon S3, Athena, and this is the proposed methodology. This will be properly and explained by Harshal in later on. So what are the requirements for our project? So software requirements that we are having is the Power BI tool, MySQL, Apache Spark, Apache Hadoop, and Google Form, View Manager, Amazon Web Services, and Hadoop. So these all are the requirements. So what are the techniques that we are using? So we will be using logistic regression techniques and algorithms, logistic regression, support vector classifier, Naive Bayes, decision tree, and random forest. Out of this, all these five, you will get to know later on that which has the main results output. So you will get to know later on. So our resources requirement in phase 1 implementation were Windows operating systems. That is a laptop basically containing Windows operating system, 8 GB RAM, 4 core i5 processor or above, and Linux operating system, 8 GB RAM, 4 core i5 or above. In phase 2, we were the resources were Google Drive storage, Amazon S3, and Amazon EMR, Amazon Glue, Amazon Athena, and AWS CubeSite. So this all will be explained later on in full detail explanation later on. So impact analysis. So social impact analysis, that is positive side, as you can see, is the early diagnosis. So in this, what is that? You get early diagnosis. So there is no, you need to go and check up. So there is no need to check up, and you need to stand, because this is a pre-diagnosis tool. And let's say here our model is 80% efficient. So out of every 5 patients, the model is correct for the 4 patients. So this, and for better healthcare, that is we are also going for better healthcare system. That is instead of several up and downs going to hospital and coming, so we are giving like this is an you can say a smart health record maintenance system is also there, and decrease in mortality rate as people come to know in earlier stages that they are having heart disease, so they can take precaution first only, because precaution taking before is very much good, and that can decrease in mortality. So negative impact that you can see in social is, that is loss of blue collar jobs, such as the surgeon who has to do, like who is to get the patients like 4 to 5 on the daily basis, that number will get reduced, and potential to create havoc in the society. And privacy concern, like if there is by chance any data leaks or something, that can cause a trouble to this. And environmental positive impact, reduction in medical waste. As you know, the medical waste is generated in huge amounts. So here the medical waste will be not be generated at all. It will be 0% medical waste, as you can say. And decrease in environment pollutants, that is in environment pollutant, that is use carbon dioxide and everything for the like X-rays and all the carbon dioxide that is get polluted to environment, that also harmful chemicals are not released here. And the negative impact is increase in energy consumption, that is as the system will be working 24/7, therefore as system will be working 24/7, so there will be energy consumption increase and more carbon footprint, as the heat will be released from the system, that is heat exchange will be taking transfer, so there is a more carbon footprints there. So this is the impact analysis. And professional ethics to be followed, that is information validity. We will validate all the information storing here with the help of Google data forms and minimal information acquisition. So the precise data will be given to everyone so that there is no chances of any data leak or integrity or breaching. And scalability, there is high scalability of these things. So let's is confidential and there will be a confidentiality that is between patient and the you can say doctor. There will be a confidentiality maintained. There will be also a transparency. There will be no data breaches here, and accountability, that is as you can maintain accountability, that is you can maintain a record of the people, or sorry, maintain the record of the patients there also. So these are the professional ethics to be followed. So from system implementation, it will be taken by Nikhil Raj Rinde and Harshal Fegde.
Before discussing the architecture for the project, I would like to discuss the dataset that we have used. So here is the dataset. We are using heart disease dataset from UCI repository, which was collected in 4 different hospitals. One is from Hungary, another is from Zurich. The rest 2 are from Long Island and Cleveland. Yes, Cleveland dataset is one of the widely used datasets for coronary heart disease related machine learning models. The dataset is even available on Kaggle. Yes, the data is really well explained at Towards Data Science article, so I'm using it directly. The dataset contains 303 entries and 14 columns, out of which 13 are independent variables and 1 is dependent variable. That is what we are trying to predict. Dataset contains age, sex, chest pain type, resting blood pressure, serum cholesterol, resting ECG as the features. These are general features that can be easily tested for. The rest of the features are less invasive tests. There are 5 categories in our predicting variable, which range from 0 to 5. For the sake of this project, we have considered 0 as absence and all other values as presence of heart disease. This is the Google form that I'm using for collecting my data from patients. Here I have mentioned all 13 independent variables. This doesn't have the predicting variable. We will predict it via machine learning. This is the CSV file that will save all my data inside it. And once this CSV file has some data, it will be then transferred to MySQL. Yes, this is my Cloudera machine. This is the CSV file that contains my Cleveland dataset. Using an SQL source file, I'm creating a MySQL table called Cleveland and loading directly via a CSV file. This is my MySQL console. As you can see, I have sourced this SQL file here. So all my data has been loaded. You can see Heart A dataset inside my database list. Within this Heart A, I have Cleveland dataset. This Cleveland table has 303 entries in all. I've created a primary key called entry number, which is auto incremented value for number of records inserted. Now using a source file, I'm transferring all my data into HDFS. From MySQL to HDFS, I'm using Scoop as an ETL tool. So you can see this is the output for my Scoop ETL. Here you can see there were 4 jobs, and inside every job there were 4 partitions. Number of splits is equal to 4. So with number of splits is equal to 4, you can see the data inside my HDFS. I have done it on a warehouse directory called demo for demo purposes. It is inside my Heart A, but let me show you the demo. So inside my Cleveland database, I have 4 partitions. These 4 partitions were because I've used 4 mappers. So these 4 mappers, they run parallelly and retrieve records. So inside every mapper, you can see, yes, this mapper was used for first 76 entries out of 303 entries. Yes, this is my Jupyter notebook where I'm running my Spark course. So here I'm importing find Spark to find where my PySpark is installed. Uh, Later on for pre-processing, I'm importing pandas, numpy, c1 and matplotlib. This is the PySpark module that I'm importing. I'm creating a Spark session out of it. Yes, here I'm importing the data to a CSV file, which is my Cleveland data set. The columns are being added. You can see a head of my CSV file here. This is the pre-processing step that I'm doing. So I have 6 empty values, and out of these 6 empty values, I'm pre-processing it. I'm filling it via mean. So once that is done, uh, for the last predicting variable, I have 5 categories, and out of those 5 categories, I'm considering 0 as absence of heart disease, that is 0, and all other categories as presence of heart disease. So I'm making it a binary classifier. Here is the description of my data set. You can find all the like count, mean, standard deviation figures over here. Yes, this is my last predicting variable. As you can see, for 0 values, there are 164 entries, and for 1 values, it is 139 entries, so almost balanced. Yes, this is the correlation diagram that I have plotted. Here, I'm creating a Spark data frame out of Pandas data frame. So you can see how the variables are dynamically typecasted. This is the first 5 rows of my Spark data frame. Yes, here I'm importing the columns. With these columns, I'll be using a vector assembler to gather all my features in an output column called features. Yes, these are my features. These are the top 3 lines. Yes, from these features and prediction variable pred, I'm creating a 70-30 split. Yes, so now here comes my machine learning model. So this is logistic regression. I imported logistic regression. I've fitted the model with training data set. This is the ROC curve for logistic regression. This is the prediction values that you can see. So for every 0, my model is predicting 0. Same for all others, and for 1, my model is predicting 1. So you can say that my model shows an ROC AUC score of 92% for training set, and for test set it shows 91.52% accuracy. Yes, this is my second machine learning model, that is SVC, support vector classifier. So with support vector classifier, I'm doing the same thing. It's just that here it doesn't give probabilities as an output. So the summary doesn't have probabilities. Yes, my support vector classifier was able to predict correctly for 89% of the training set and 94% for the test set. Yes, this is another way of saving my model. So whenever I want to load my model directly, I can load it if I have saved it earlier. And with this loaded model, I can use it directly to predict new values, to predict transform on new values. Yes. So this is my third model, that is Naive bias. So as you can see, I've fitted the model with this. I've used a Gaussian model type, and the smoothing is 0.01. All these values were found out by using k-fold cross validation. Yes, k-fold cross validator. So yes, my ROC curve for naive bias is 76% for training set, and for test set it is 77%. This is decision tree. My decision tree takes max depth of 5, and here are the train column and the predicting variable. Yes, here again it gives probability. So for decision trees, my ROC for training set is almost 86%, and for test set it is 79%. So quite low, right? But when we do it by random forest, the accuracies tend to increase. So here, with the help of hyper tuning, I'm trying to achieve that. Here I'm using impurity as entropy instead of gaining, and the number of trees that I have trained is 40, and the max that I'm going for is 6 nodes. So here, if you look at the last figures, the training set for the ROC score for training set was 99% correct, and for test set it is 92%, as opposed to just a single decision tree. So this really works out.
So this is a flowchart of AWS. In this, first the collection of data will be done using a Google form, which will save over the Google Sheet in a Google Drive. To upload the data from Google Drive to S3, we will use a third-party app like Cloud HQ, Wonder Cloud. So I'm switching to the AWS console. So this is the console of AWS. In this, we will go to the service S3. So we already have data uploaded to S3 in one of the bucket called hard disk prediction. So this is the data. This is the file we have uploaded. The process level end. Then this is the bucket and the S3 in S3. Then we will switch to EMR. The data is processed in Amazon Elastic MapReduce service. It has a big data tools like Apache Spark and Hadoop. The prediction as well as the original data will save back in S3 after the process. So let's see how we can create a cluster. So we have to give the name of the cluster here. There's no need of logging here, and this will be default. And we are using the Spark and Hadoop tools. Then in this instance type, we are using the M4 large because it has 8 GB of RAM and 32 GB of EBS, which is elastic block storage, which you can get. And we are using number of instance will be 5, 1 master and 4 core nodes. We have the option of cluster scaling also based on our workload, and we have to put the EC2 key pair for the security purpose, so which I already created. This S3 Marshall 26. If as soon as I start create a cluster, it will charge. It will charge per month per hourly basis. So let's switch back to the glue, AWS glue. So once this data is there in a S3, the AWS we will be able to import it using a AWS glue. For this, in this AWS glue, we have data tables, connections, crawlers. So we'll switch to crawler for data fetching. In this, we have to add a crawler. We have to give the name of the crawler. So I'm 26 next. This will be default. as data store is in the S3, so we have to browse this file. We have to select, then we have to next. We have to choose the existing IAM role, which I have already created, Harshal26. Then next, and this is frequency, which can be hourly, daily basis, but we will run on it demands. Next, we have to give the database also. So we have to create Harshal. Go next. So this is the preview. We have to finish. So it will take time. As our crawler is ready, so we have to go inside this crawler and we have to just run this crawler. So it will take time. As the status is ready, as the status of a crawler is ready, so the data is fetched into this. So we'll go to the next service called Athena. Basically, it is used for running the SQL query. In this, we have a data source called AWS Data Catalogs, and we have created a database that is Herschel. And we have one table called Cleveland dataset. In this, we have different attributes like age, sex, CP, etc. If we run this query, it will cost us, but I have run this and I got the output. This is the result which you can see on the screen. Now, for the analytic parts, there's a service in the AWS called QuickSight. Let's go to that. As this QuickSight is also not in a free tier, so it will also cost. In this, we have to create an account. So for alternative, we'll switch to the Power BI. So in this, we have to import a data. We can have an option here. It will take time. Yeah. In this, we have the option of Amazon Redshift. With the help of this, we can import a data. So basically, it will look like this. We have a data set here, and this is a dashboard we have created. And we have used some of the parameters like age and chest pain. If we change this parameter, there's a gradual change in this parameter also in these blocks. You can see this. Yeah, it's changed. So the Power BI is used for visualization and for data cleaning also. Okay.
Yes, so as we discussed in the Spark implementation about logistic regression, SVC, web bias, decision trees, and random forest. So let's do a quick discussion about that. So I had 13 features for my training, out of which 8 were categorical values, and one of them was my predicting variable. So only one predicting variable, which is a binary classifier. Yes, so for training set, I have 212 samples, and for test set, 91 samples, which are nearly 70% and 30% of my data set. That is 303 entries in Cleveland data set. Yes. So comparing the ROC score for all these models, so we can make an inferential here that logistic regression was able to do it correctly for 92.25% for training set, and random forest did it really well, that is 99.71% for training set. Based on these values, if you look at test set, SVC was able to do it for 94.1%. So SVC model was one of the is among the best for test set, and random forest did well too as compared to decision tree. So in comparison with one tree, random forest, which was almost 40 trees, so random forest did well. Yes. So now we are in conclusions and future scope for the project. So as we move forward, as this project moves into deployment stage, this project can be deployed as a pre-diagnosis tool for heart disease, like with increasing number of records, with the data that we are dealing with, if the quality is increased, we will be able to increase our accuracy that much, right? So with more number of data and more accurate data, we'll be able to build a more reliable model on it. For future scope, we're putting automation. So right now, currently, we all did the whole process manually. So we were running code somewhere. We were doing the whole infrastructure setup on it. So this automation part, we took it to AWS. AWS deals with all the infrastructure guidelines. It creates pipelines to make it completely, like, not completely, but almost negligible for human care. In the second future scope, what we're talking about is generalized model for disease. So as we move forward, as we have more data about this disease, we can make a inferential model based on this. So let's say if I have a patient who is having high blood pressure, so every layman person knows that this guy is supposed to have like he's supposed to have some problems related to heart, because his blood pressure is high, so he must, like, he is prone to having some kind of heart ailment. At the same time, with high blood pressure comes diabetes. So diabetes patients too have that symptom. So based on this, we can make a generalized model on the current data, and with the increasing data set, we'll be able to do it. Yes, these are the references that we used for our paper. Most of these papers are from IEEE from 2015 to almost 2021. Yes, thank you for listening to us.